Okay, grade 11s, in this lesson we're going to be focusing on the proofs of theorems. Now, up to now, you've been given, for example, theorem 1, and we used it, but now what we're going to do is we're going to actually physically prove theorem 1. And what does theorem 1 say? It says the line segment joining the center of a circle to the midpoint of a chord is perpendicular to the chord. So we want to prove this theorem. In an exam, they'll say to you, prove the theorem which states that the line segment joining the center of a circle to the midpoint of a chord is perpendicular to the chord. So let's have a look at a circle here. What are we given? Okay, if I said to you, tell me what are we given, automatically you can see that AM is equal to MB. And what do you want to prove? You want to prove that M1 is equal to M2 is 90 degrees. In other words, that OM is perpendicular to AB. So you're given that AM is MB, and you want to prove that M1 equals M2 equals 90 degrees. In other words, OM is running at right angles to AB. This is theorem 1. The line segment joining the center of the circle, that's OM, which joins the center of the circle to the midpoint of the chord, that's M, is perpendicular to the chord. Now, the way to approach this is really congruency. Now, I'm going to draw AO, I'm going to construct AO, and I'm going to construct OB. Now, if you look at this, we've got triangles, two triangles here, in which AO is OB. Those are the equal radii. You're given that AM is MB, and notice that you've got a common side OM. So it seems like these two triangles can be proved to be congruent, as you did in earlier years. And if so, then what can you conclude about M1 and M2? They would be equal. But still, then, how do we then prove that they're both equal to 90? Now, watch this. Watch the space. It's absolutely brilliant. I'm going to start off by proving the two triangles congruent. So I'm going to say, in triangle OAM and triangle OBM, if you look at those two triangles, OAM and OBM, what do we know? Well, the first thing, we know that OA is equal to OB. Equal radii. The radiuses of the circle are equal there. Okay, the second thing is that AM is equal to MB. Why? It's given to us that AM is equal to MB. That's given. Okay, and then we also know that OM is equal to OM. That side is common to both the triangles. You see, OM is common. So in other words, when you've got this situation, we automatically know that triangle OAM is congruent to triangle OBM, and the reason for that would be three pairs of sides equal, corresponding sides equal there. And if the triangles are congruent, if OAM is congruent to OBM, automatically M1 and M2 will be equal. So therefore we can say M1 is equal to M2, and that's because the triangles are congruent. Okay, but now here comes the magic. How do we prove that these two are each equal to 90 degrees? Well, now think about it. What do you know about M1 plus M2? M1 plus M2 is 180 degrees. What is the reason for that? Well, that is going to be adjacent supplementary angles. Okay, that's angles on the line. They add up to 180. But now we know that M1 equals M2. So the only two equal angles that add up to 180 would be 90. So therefore, automatically, M1 is equal to M2 is 90. Two equal angles that add up to 180 would be 90. And therefore, OM is perpendicular to AB. And there you've proved, beyond a shadow of a doubt, theorem 1, which says the line from the center to the midpoint of the chord is perpendicular to the chord. The line from the center to the midpoint of the chord is perpendicular to the chord. Now, if you look at the converse theorem, this wouldn't be really asked in an exam, but to do it is actually very, very useful, and it also involves congruency, but another case. So I think it's worthwhile doing it, but you won't really be getting that in the exam to prove. But let's see, it says the perpendicular drawn from the center of a circle to a chord bisects the chord. So if we look at this, what are we given in this case here? We're given that M1 is equal to M2 is equal to 90 degrees. You're given that OM is perpendicular to AB. What do you want to prove? Okay, well, let's see. You want to prove that AM is equal to MB. Now, that's easy because all we're going to do is another construction. So we join AO and OB knowing that those are equal radii. We also know that M1 and M2 are both 90 degrees, that's given, and also OM is common. Now that is very interesting because in these two triangles you've got the hypotenuses being equal, there's their right angles being equal, corresponding right angles, and you have a common side. So it looks like it's a case of RHS, right angle hypotenuse side. So let's go ahead and prove them congruent. So we can say in triangle OAM and triangle OBM, what do we know? Well, we know that firstly, if we take the right angles, M1 is equal to M2 is equal to 90 degrees. That's given to us. That was actually given information. We also know that OA is equal to OB, equal radii of the circle. Okay, so remember this gives us the right angles that are equal, the hypotenuses that are equal, and then we also know that OM is equal to OM common shared side, which automatically then tells me that triangle OAM is congruent to triangle OBM. The reason being right angle hypotenuse side. The right angles are equal, so it's R. The right angles are equal, the hypotenuses are equal, and there's a common side there. Common side that's shared. And if they equal or congruent, these triangles, then automatically you can say that AM must be equal to MB because the triangles are congruent. And this is the congruency in a different form. So what this is saying is if you're given the right angles, then you can immediately conclude that AM is MB. Whereas in the first theorem it said there, if AM is equal to MB, then these angles are 90 degrees. So you can see how congruency plays a big role in Theorem 1, in the proof of Theorem 1. We're no longer just assuming it, we're actually proving it. And this is the proof that you always get asked in an exam. And the converse is not for exams, but it's a worthwhile exercise to do anyway.